remembered in A1 was what's Ian just like today? Life, dude, come on, man. Life's good. Life is good. It's getting warm out. Birds are chirping. Happy days, right? All righty. Hey, I walked by the pit that is our computer science building. If you right in front by ComEv, you can see the water main that they broke through. It's like an 18-inch, 24-inch main. I'm sure that was a good time. Lakes on ComEv, I'm guessing. But they keep on building. It's like, whatever. Alrighty, today, hey, coming in. What a big crowd today. All right, today we're going to work on something a little simpler today. Let's see how far I can get this out. Hang on. Not that far. Yeah, I can see everybody. So we're taking a step back a little bit in terms of complexity. I just want to talk about bitwise operations today, like using individual bits instead of bytes and so on. Yeah, so we'll do that. I was going to think of something pithy to say about it, but I got nothing. Let's hop right into it. Alrighty, so bitwise stuff. I don't know why. This is one of those topics that everyone thinks is like really complex for some reason. Maybe I'm just missing something. Like I was reading the book last night about shifting left and right and so on, and there was some really complicated math. Like it was like really out there, and I'm thinking, I don't even understand this. Like, what are they talking about? And really, we're just moving bits from one place to another. It's like I don't get the complexity of it. So maybe I am missing something. You guys get the simplified version, apparently, because I don't think it needs all sorts of math and all of that. Malik Slate, here's your background today. More of an abstract image today. No dogs today. All right. Although this morning at breakfast time, Maggie, the dog, is well loved by all the animals in the yard and the birds too. And they come and see her. Like we have a chipmunk, especially, who loves Maggie. And anytime Maggie's out, he'll come running out and sit and watch her. He didn't really come close to her. I mean, she's not going to chase him or anything, but birds too. And wrens, especially, for some reason, really like Maggie. And so today there were two wrens peeking in the back door to see if Maggie was home. I was going to let her out, but she was more interested in breakfast. So the birds had to go denied. Yeah, it's really sweet. Maggie, like I looked out once, Maggie was in the yard. It's when she was a little bit younger. She was in the yard. There was a woodchuck in the yard. And I kid you not, the woodchuck and Maggie were nose to nose, just sort of sniffing each other and saying hi. And then the woodchuck turned around, turned his back to Mags, and just waddled off. It's like he was just saying hi, I guess. She's a sweetie. Everyone knows that she wouldn't hurt them. All righty, so that's my life. It is just a paradise at home. Actually, it's very nice at home. All righty, here we go. So bitwise stuff. So C is, I've said it a couple of times, like C is we're just really into performance. Like a lot of the reasons we write in C are because we're so close to the metal. Like we're just really close to the hardware, and it's simpler to optimize things at that layer, because like if you're in a language like Java, you don't even know what machine you're running on. You're running in some virtual machine on some platform, like who knows what it is. And so you can't really take advantage of hardware related optimizations. I guess the JVM could do it, I suppose. Just a lot of layers of abstraction. Even in C++ or JavaScript or Python, like any of those higher level languages, there's a lot of abstraction. There's no abstraction in C. Like what you see is what you get, basically. And especially when we start, go down to the basement and start looking at assembly language and what assembler is the C compiler spitting out, like we're just really close to the hardware at that point. And so we can take advantage of that and really optimize code so that it's efficient and fast as possible, given the limitations of the hardware. It's just stuff we can't do in the higher level languages. It's one reason why C is so much fun. Like you just really get to, you see everything, It's like there's nothing hidden at all. In Java, like I remember writing code in Java. God, I hated Java. But you'd write a bunch of codes. Like, what does this even do? I don't know. I was told I have to have this in Java or it won't run. It's like, okay, I'll just drop that in then, I guess. But in C, like, there's none of that. You either know what you're doing or you don't. That's why when I haven't done technical interviews for a really long time, but C was always my choice for tech interviews. Like, I wanted to know generally what they knew. But when we got down into the weeds, I'd start to ask them about C, because that told me whether they understood like the underlying stuff that they were writing against or not. Yeah, public static void main. Oh my God, all that stuff. But and Malik, the problem, right, is that the IDEs know that like it's just a lot of stuff to write every time, and so you start writing, public stat, and it says, "Oh, you want to complete this?" So you said, "Yeah, sure," and then you're never typing it anymore. So how can I remember it, right? All right. So anyway, so we're talking about performance. It's not necessarily speed either. Like we're talking in A1 about embedded systems. Well, we could write public static void main blah, right, Leanna? We were talking about embedded systems like controllers, like maybe a controller for an instrument, or the controllers in a Tesla engine or something. Like a lot of that code's written in C. For like the reasons we've been talking about, like performance issues, and because it's so close to the hardware. But a lot of times in those environments, like we just don't have a lot of resources. Like memory is really limited. Maybe I've only got a meg of memory, and that's got to fit everything. Like my little operating system, I've got to fit processes in that, memory of some sort. So I might be really, really restricted on resources. C allows us to, like, as we'll see today, we're going to get down to the bit level. Like I can manage individual bits and not waste any space whatsoever. So I can write really, really tight code in C/assembly language that just I can't write in any other language because I don't have those facilities. All right. So like this, like if I'm going to store the date, and by that I mean the day of the month, 1 through 31, like what data type, what sort of variable would I create to store a date like that? Like what would I use? It's an integer value, so I'm probably going to use an int of some sort, right? A short, yeah, Jonas says probably a short. That kind of makes sense to use a short. So a short unsigned is going to be 2 bytes typically on these machines. So an int is 4 bytes, a short's going to be 2 bytes. Well, how many values do I have in 2 bytes? I've got 2 to the 16th, right? 8 bits in each byte. I've got 2 of them, so I got 16 bits. 2 to the 16th is 65,535. Sorry, 65,536. That's a lot more than I need, right? Like that's just, I'm wasting, how many do I need? Let's say 1 through 31. So the next closest power of 2 is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 16 is not enough. 32 is the next one up. I only need 5 bits to store values between 0 and 31. Like, why don't I just use 5 bits for the date? Makes perfect sense to me. Day of the week, I can use how many days of the week are there? 7, right? So I just need 2 times 2 is 4, times 2 is 8. I can do that in 3 bits. Store the day of the week in 3 bits. Like, I don't need all of that space. Even if I have an unsigned short, that's 2 bytes. That's way more space than I need to store the date. So it'd be really nice if we could condense that down into just the bits that we wanted to. And what we'll find out today is there are ways to do all of that. We can use logical operators, we can shift bits around, we can mask stuff out. We'll end up writing bit fields where I can define individual, basically variables that are a varying number of bits. Like it's a really, really fine-tuned control over the underlying memory storage. It's pretty cool. Let's look at the shift stuff first. So these are the simplest operators, shift right and shift left. It's basically shift something this many bits. So for example, if I've got some value here and I do a shift 3, it's going to take the bits, and which one am I going to the right? It's going to move the bits to the right once, to the right again, and to the right again. It's going to move them 3 times. And then what happens is, as I'm shifting those numbers around, like I'm creating holes, right? So if I'm moving everything to the right, all the bits are moving this way. Well, like what's going to happen on the left side? Like if I've got this, for example, text. Let's write one out real quick. 1, 2, 3, 4, 5, 6, 7, 8. So if I shift that once, it's going to end up, I'm shifting all those bits this way to the right. What I'm going to do is, as I'm shifting, when I shift away and it creates a hole, I'm just going to stick a 0 in there. So if I shift to the right, it's going to be, here we go, 0, 1, 1, 0, 1, 0, 0, 1. There used to be 1 there, right? If I shift it again, I'm going to shift in a 0 on the left, so I'll have 0, 0, 1, 1, 0, 1, 0, 0. Now if I shift it again, another one comes in, 0, 0, 0, 1, 1, 0, 1, 0. See what's happening? So as I go to the right, I'm filling those holes with zeros. If I went the other direction, if I shift to the left, so this one's going to go that way, it's going to be, this is hard, 1, 0, 1, 0, 0, 1, 1, 0. So basically, this bit became that bit. They all shift left once. That bit became this bit, and so on. And again, I'm just going to fill those holes with zeros. So if I shift this again to the, to the left, going this way, I'd end up with 0, 1, 0, 0, 1, 1, 0, 0. So I'm filling those holes with zeros. And the bits, somebody asked me where the bits go when they fall off the end. They go into bit limbo. I don't know. There's this big bit bucket in the sky, and they all go into the bit bucket. They just disappear. You lose them. Cool, huh? I guess pretty easy. Bit bucket, oh, that's a term. Bit bucket is a term for sure. So the bits fall off the end, and we shift zeros in to fill in the holes. For example, here I've got, here's an unsigned short, 2 bytes. 65,535 means it's all ones, so that is FFFF in hexadecimal. If I shift them to the left, I'm going to shift them to the left, and I'll have 3 zeros on this end, and all my ones go that direction. If I shift it back to the right, so I take this value and shift it to the right, now these zeros are going to fall off the end, and I'm going to add zeros to the left side as I shift. So here's a problem. There's always a problem, right? It's like computer science. We solve one problem and create 2 more. It's sort of binary in that way. Here's the issue. If this were a signed value, Ian, we'll get to that. Ian asked what we usually use this for. We'll show you in a couple of minutes. If this were signed, so it's a signed integer. In signed integers, the sign bit is this one. So the first bit in the byte is the sign when I'm signing an integer. And by signing, I mean, if there's a 1 there, it's negative. If there's a 0 there, it's positive. If I'm shifting around, I'm going to lose that bit. Like here, for example, I had a 1 in that location, which would mean a negative number if it was signed. And then when I shifted to the right, I fill with zeros, right? So all of a sudden, I've lost the sign information here. That's not cool. The reason that we use unsigned values for shifting is just that. So shift unsigned values. Even worse is the bullet in front, this bullet, whether that signed bit, so if I had a signed value here, so this was, again, a signed value. So if those are signed, it depends on what CPU you're on and what operating system the CPU is running with, as to whether that bit will be preserved. On some architectures, some platforms, it'll keep the bit for you as you shift to the right. It just maintains that sign bit so you don't lose the sign information. On other platforms, it does this. It moves the sign bit out of the way. Well, the problem is, like, we don't have any control over that, right? Like, is the CPU that this program is going to run on, does it preserve the sign bit or not? Like, I don't know. How am I going to know? I think I find out, I guess, but it's implementation dependent. I suppose we could write some code like if-def so I could see what the platform was, like look at all the platforms and how they handle it, have if-def statements around code so that I could preserve that bit if I needed to. But the easy way to do it is just do unsigned shorts. It's a source code compatibility issue. Actually, it's just a compatibility issue to begin with, portability. I can't take the code and assume it's going to run on some other platform. You know, it just might not. It might treat it differently is the problem. That's actually the case in a lot of C. In other languages like Java and Perl, I always say Perl and I mean Python. It's because I wrote so much Perl code in the day. Like Java and Python and even to some extent C++, like there's so much abstraction happening that like we don't even know that this is a problem. And like those systems like Python, it just takes care of that for us. Like it knows, it's got all of the if-defs in the Python interpreter to figure out, oh, do I need to preserve this on this platform or not? If it's doing shifts under the hood or something. Like in C, we don't have that abstraction, we don't have that luxury, and so we have to think about it is the problem. And it means that we spend a lot of time, especially if we're going to distribute our code, making sure that it runs on a lot of different platforms, little endian platforms, platforms that preserve the sign bit and so on. These are all things we have to think about in C that we don't have to think about in other languages because it's hidden from us in the other languages. So best practice, if I'm going to do shifting like this, just use unsigned values, and then I don't have to worry about it. The other thing is that all of these operators that we're going to look at, all these bitwise operators, they have really low precedence. So the order of operations, they're the lowest, like it's hard to find something lower than one of these bitwise operators. So these things have much lower precedence, the shift operators, than plus, for example, which itself is relatively low. And the problem is, like, if I write this and I really meant this, those are two really different things because the plus is going to happen first. And then 42 is going to get shifted to the right. Actually, value is going to be shifted to the right 42 instead of 2, right? Is what's going to happen here. Like, that's not cool. We don't want that. So we use parens to indicate intent. And I went on a rant in A1. I can't remember where, so I'll just rant here. It's just not a rant, it's just advice, like a life pro tip. Always use parentheses. I mean, it's one thing to know the order of operations, like the precedence in the language that you're writing. But like, for example, if let's say I'm 1,000 lines into this code, I'm debugging somebody else's code, which is pretty common at work. Like you're almost always given somebody else's code to work on because, two eyes, right? If I see this, I'm gonna have to look stuff up. I don't remember order of precedence all that well, especially like specific orders of precedence. Like who remembers any of that? I'm gonna have to go and figure out what's meant here. It's pretty obvious in this case, like you're not gonna shift something 42 probably. It probably did mean 2. But what if it was 2 plus 4 or something? Like that's a little more ambiguous. I'm gonna have to go look it up. You're basically wasting my time, forcing me to look this up so I can figure out what your stupid code did. If you just use parentheses to indicate what you wanted, this is what you wanted, probably. That's probably what you wanted. Just put the parentheses in. Now there's no ambiguity. The parentheses say exactly what you wanted the code to do. You're not relying on your memory of precedence of operations. I don't have to look it up. It's obvious what it's doing. Just use parens. And if anyone ever asks you on an interview, what's the order of precedence, for arithmetic operators in C, you don't have to know. On the interview, you just say, order precedence is like, it's always different, like in different languages and so on. What I do instead is I just am very explicit in my code. I use parentheses to group operations so that I know exactly what order they're going to run in, and then I don't have to worry about it. That's the answer you're looking for. If I heard somebody say that and their resume said they graduated from BU, like I'd probably hire them on the spot because, I mean, A, they're from BU, so I know what they know. And when you say that, it tells the interviewer that you're thinking beyond like just the code. You're thinking about maintainability and about design and higher level stuff that's going to make you a more valuable employee, I think. So that's my life pro tip for the day. Use parens. Just use parentheses everywhere. It's an extra keystroke. It's going to save you more time than the keystroke, I guarantee it. A lot of stuff on that slide. All right, so hey, Ian, why do we want to shift bits around? A little bit of hand waving on this one. Shifting left is the same as multiplying something by 2, and right is dividing by 2, which is faster than actually doing multiplication usually, in powers of 2 at least. It's the algorithmic requirements. That in fact does not say shift bits around. Nobody at A1 noticed that. Who said that? Christine. Thank you. Let me just put an F in there. Can I have an F for the shitting bits? Thank you. Shift. Damned autocorrect. All right, so like shifting stuff around. Honestly, I don't do it, Ian. I don't do a lot of shifting stuff around just for shifting. Like even multiplying by 2, it's like, how often am I going to multiply by an exact multiple of 2? Probably not very often. We'll get to some stuff where it makes sense to shift things around. Really, this discussion is more about just treating individual bits as individual bits. And the shifting stuff is like, it's an operator we need to talk about. And we'll actually use it. We'll use it to create masks and so on in a couple of slides. Yeah, Ian, only do a shift if you're required to. It's one of the solutions looking for a problem. Now that said, there's tons of shifting going on, and like if you look in kernel code, they're constantly shifting stuff around, but mainly they're creating masks and testing values by using the shifts. You're not going to wake up some morning and say, well, I'm going to write some shift code today, by golly. All right, we'll get to shitting bits around in a sec. Let's look at the logical operators. So these logical operators are the same as the C ones that you know in other languages, like ampersand. Ampersand is an and operation in C. In Java, actually every language is and. Same with or. It's pipe. Typically 2 of those things when we're in sort of byte level in C or variable level. Exclusive or, I think exclusive or looks like that in C. They're pretty close. Like we're still doing logical operations, so logic is logic. Don't assume though that like the C version, like the ampersand of and, will do exactly the same thing on a set of bits that the individual and does. The way I remember these is there's only a single ampersand here, and so it's for a single bit. Single pipe there is for a single or, and so on. XOR gives you flashbacks to 131. Actually, it should give you flashbacks to 101 if you took 101 with me, because we talk about logic circuits, and we realize, oh, exclusive OR looks like an addition or something. Yeah, so They're pretty much the same. And that's a pipe character, by the way. That's not an L or something or a 1. That's the pipe character. It's above the return key on my keyboard. Here's what these look like. So I've got X and Y over here, X and Y. Here is X and Y. So you can see that 0 and anything is 0. 0 and 1 is 0, 1 and 0 is 0, 0 and 0 is 0. The only time I get a 1 with an and is if both sides are a 1. So 1 and 1 is 1. On an or, it's sort of the opposite of that. Anytime you see a 1 on either X or Y, you're going to get a 1 on X or Y. So I sort of remember these as, the and is, it's one, this one and that one. This one and that one gives me a 1. For an or, it's this one or that one, or both gives me a 1. I never knew if those made sense. De Morgan, yeah. De Morgan's overrated. Nans, they should all be Nans, right? Here's exclusive or. Exclusive or, my explanation is always around a nightclub. It's a very exclusive nightclub, and the door is really, really small to get in. And so if one person tries to get in, that's cool, that works. And if another person tries to get in, that works. But if both try to get in, it's very exclusive. If 2 people try to go through the door at the same time, no, you can't. That's an exclusive or. So exclusive or, it just looks like, yeah. Actually, that's the and or an addition function, right? I can do a sum of 2 bits using an exclusive or. So those are the operators. They look, nothing has changed. They look just like they did when they were invented by Chuck Boole or whatever his name was. They'll look the same in every language. I've got a, Jonas says, why is this not the generally accepted way of teaching exclusive or with the exclusive nightclub? I guess the other professors haven't been to exclusive nightclubs. So actually, it reminded me of a story I told in A1 at this point, which is I literally was cleaning out a desk last week, and I came across a birthday card from a few years back. It was back when I was traveling quite a bit. My wife took me to New York City to celebrate my birthday, and she booked us at the Waldorf Astoria. So we walk into the Waldorf. She had booked all this stuff, but I was the one who was traveling just all the time, and so I had status like crazy. And so we check in, handed my ID card over to the clerk, and she's type. She looks up, she goes, "Mr. Donham, welcome to the Waldorf Astoria. I've moved you into an executive suite." And my wife is like, "Whoa!" And so we went out and did a little bit of stuff and came back, and there was a card for me at the desk. So I was like, "Oh, that's nice." I thought my wife had left me a card. No, the card was from the staff. It was, "Dear Mr. and Mrs. Donham, we have placed champagne in your room as requested, but no birthday is complete without a cake. So we've baked you a cake." They literally baked me a birthday cake and stuck it up in the room with some chocolate-covered strawberries and champagne. It was like, and my wife is like, "Who are you?" It's like Bond, James Bond. It was fun, I'm one of those people who just love that, because I was just flying so much. It was always first class because I had all the points, and just good times. If you guys are like looking for jobs, especially right out of college, consulting is a really fun job to have out of college, especially a place that where you get to travel, because it's, all expenses paid. You get to stay in nice places. Most places let you keep the points, so you end up with lots of status at hotels and on airlines and so on. I don't have any now because I haven't been traveling for 2 or 3 years. Anyway, that was a good trip. Oh my God, I completely forgot about that. So we're in New York City, right? It's my birthday weekend. We're in New York City. We're walking down the street, and I see something shiny on the ground. I lean down to pick up the shiny thing because that's just who I am. And it's a little foil thing that must have been a sticker on something, gold foil. It said, "Happy birthday." It was so crazy. I assumed it was my dead grandmother wishing me happy birthday. But anyway, sorry. So that's and exclusive or. This is why my lectures always run so long, I guess. There's also a complement operation. This is a ones complement. So it essentially flips the bits. It's a tilde, by the way. Tilde, not a dash. Sometimes it's hard to see. So it's a ones complement. It takes every one and flips it to a zero, takes every zero, flips it to a one. So this thing, do a complement on it, and it literally is just the opposite of what it was. I can, the way I use it this way typically. It's when I need to set up a whole bunch of bits at once. Like here, tilde zero, it doesn't matter how big the word is I'm working with. Zero is zero. So if it's an unsigned short, it's going to be 2 bytes, all zeros. If it's a long or something, it's going to be 8 bytes, all zeros. Like it doesn't matter what kind of variable I'm looking at. If I do a complement on it and it's all zeros, they're all going to be ones. So across the entire data structure. So I'll do that often when I'm setting up a bit field. I just need to set a whole bunch of bits at once. That's a quick way to either clean them out, set them all to zero, or set them all to one. And then if I need to like have a specific set of ones and zeros, I could do something like this, like F, thank you for the Fs. F in hex is, in binary rather, is 1111. And so again, it doesn't matter how big the data structure is. F is 15. There's going to be 1111 in the last 4 bits rather. So it's going to be a bunch of zeros and then 4 ones. I can flip them like this. If I just flip 0F, that gives me a whole bunch of ones and the last 4 are zeros. Like, is that useful? And yeah, maybe it's useful. I use this a little more often to clear bits, but even that could be useful too, I think. If I knew I had a specific bit pattern I wanted, it's just easier than setting them up individually. Yeah, again, you got to worry about that, the sign bit, right? So if I'm flipping them like this to that, all of a sudden I got a negative value if that's a signed number. So I just got to worry about that. Some machines used to store stuff in ones complement. We'll actually we'll probably talk about two's complement next week. There's a system called two's complement that's a little bit different. That's what most modern machines use. You're probably not going to run into one's complement in memory anywhere anytime soon, unless you go over to the MIT FLE, which I think starts up in April. Is April the first one? Maybe May for sure. You might, the MIT FLE, if you haven't been there, I mentioned it before, just down in Kendall Square, sorry. So much fun. Just like if you love computers or audio stuff or lasers or telescopes, if it's techie, man, they've got it. Like bins of tubes, if you want to build a tube amplifier or whatever, tons of parts, tons of whole machines. You can buy those colored iMacs, those fancy little iMacs with the translucent covers. They usually go for 25 bucks. I bought a, the old cheese grater Mac Pros. Oh God, they were beautiful machines. Big honking aluminum case, twin Xeons in them. I bought one of those for 20 bucks the last time I went to the FLE last year. It's a lot of fun. Anyway, you might run into a PDP-1 over there, although probably not a 1. I've seen PDP-11s over there for sure. Actually, I've seen a PDP-7 over there also. Malik, it's a Kendall Square, usually around the engineering building and the computer science buildings. You'll see posters for them. Next time I see a post, well, let's go find out when is the next one. MIT FLE Market. When I lived in Alston, or Brighton rather, I was there every month. Here we go. Important dates, geez. We're still hoping, MIT's not resolved, geez. So they don't even know if they're gonna run them. I assume they're gonna run them this summer. If not right away, at least late summer, right? Oh, here we go, 2021. They canceled April and May. June 20th, it looks like. Anyway, just take the red line to Kendall. and follow the geeks. Like just look for the dudes in baseball hats and t-shirts. They're all going to the MIT flea. All right, so that's Bitwise complementing. All these operators, we talked about precedence, so they do have an order of precedence. Like again, don't trust your memory. Just use parentheses to mark exactly what you want to happen. Don't trust your memory. In fact, they shouldn't even have order of precedence. They should just force us to always use parentheses to indicate intent. I guess that'd be Lisp. They're compound operators, so I don't have to have a second variable, just like plus equals and times equals, minus equals, and so on. So here I've got this unsigned short. It's got an F in it, which is 15. Excuse me, I can do an and equals with 1 that essentially takes the value, it takes a 15, ands it with 1, and then stores the result back in value. So if I'm doing an and with 1, 1 is just 0, 0, 0, 0, 0, 0, 1. So there'd be a 1 here at this last bit. 1 and 1 is a 1. 0 and 1 is zeros. So I would just see that bit with this mask, or with that 1 mask. So using individual bits,
Sorry.
it's actually really common. I do this all the time in C, or did, to use a single bit to indicate something. Maybe that bit indicates the success of an operation, the color of something, whether it's been processed or not. Like anything that has like binary values, it's either this or it's that. That's a perfect opportunity to use a single bit to indicate that value. If we're going to do that, like it's just like a semaphore, right? We need to, hang on, Jonas has a question. Why is it 1 and not 1, 1, 1, 1? Because it's an and. So it's basically, I'm doing this. I've got that, and if I do the and, 0 and 0 is 0, 0, 0, 0, 0 and 1 is 0, 0 and 1 is 0, 0 and 1 is 0, 1 and 1 is 1. That's why. Anyway, so just like a semaphore, I need to be able to set a bit and test a bit and also probably clear a bit. I thought 1, oh no, it's actually just the literal number 1. So that's the number, whoops, that is the number 1, which in binary is that. I get more joy reading the chat in here than I think I should. It's just fun to read the chat. All right, so we need to do these things. We can generalize it with a shift, and somebody asked about like why are we even shifting? Like this is where I usually use shifting. So here's if I just want to store some values. Oh shoot. Yeah, this is just an aside. Sorry, I don't know why it's in this order. Just a really quick aside. We'd like to be able to do this to indicate a binary value 0b, just like we use 0x for hex. Unfortunately, it's not part of the spec, the C spec. And so some compilers do that. GCC allows it, I believe. Some compilers don't. They'll kick an error out if you try to do that. For me, and my understanding is that the next approved spec of C will have this notation in it. So at that point going forward, like we can use this, on an ongoing basis. It's just easier for me to see that this is a bit, like a bit field with bit values in it with 0b. Otherwise, I got to translate it to a number. If I'm translating to numbers, I almost always use hex because it's really simple to get from hex to binary. You literally just take each hex digit and write the 4-bit value for that number. So C is always 12 in hex. It's 0 through 9, and then A, B, C. So 0 through 9, 10, 11, 12. C is a 12. You just write a binary 12. That's 8 plus 4 plus 0 plus 0. 8 plus 4 is 12. So that is that value here. If I had like an E, it was EC. What's E? E is 14. What's 14? 1110. I could just write it that way. So it's really easy to bounce back and forth between hex and binary. So when I'm forced to, let's get a hold of 12, huh? When I'm forced to use numbers that aren't binary, I typically will do hex. 0, 0, 0. That's 12. And that was 12. So I'm typically working in hex. On a couple of slides, I use this binary notation just to make something clear. The problem with it is that it works in GCC. It might not work on other compilers. And so if we use that in our source code, that source has become non-portable. I can't give that source to somebody else and assume it's going to work on their machine with their compiler because, oh, this is just a special thing that GCC did. You know, once the spec is in place and we're all moving toward, I don't know, C22 or whatever happens to be, whatever it's going to be, then we can all use the binary notation like that. But most of the time, we'll just be working in hex like this. All right, let's talk about setting a bit. So to set a bit, I can just OR the location with a 1, because 1 or anything is just 1. 1 or 0 is 1. 1 or 1 is 1. So if I want to set a bit, OR it with a 1, and I'm guaranteed to get a 1 in that spot. So for example, I might do this. So I've got a 1 here. Should be a 1 or a 0? Tilde 1. Will that just give me all zeros? I think that gives me all zeros. I'll have to check that and see. But this gives me all zeros, and I'm just sort of resetting everything to a 0 here. And then I want to set the third bit. So all I have to do really is, if all these are zeros, actually it's like this. I've got a bunch of zeros. I want to set the third bit to a 1. I'm just going to OR it with the 1 in that position. So the value had zeros in it. I OR it with 1, 2, 4. Well, 0 or 1 is a 1. So now I get this value down here after that. Same thing here, set them all up on zeros, and then just shift. So do the same thing. I'm going to do a shift here. That shift gives me 0, 0, 1 right to left. So it gives me this value. And then now I've got this value basically. Now I can do the OR equal just as I did up here and set that bit as I wanted to. What is it? One earlier was all zeros, 1. Yeah, Jonas, I don't know. Do I have time to check it? I don't really have time to check it. Yeah, well, that might not be, that might be a 0. 0. Well, certainly this will give me all zeros, right? That's just 0 all day long. I think the notation is that will give me all zeros. It's like a little shortcut. You know what? I'll play with this after lecture and correct these slides if they're not correct. All right. So that's setting a bit. To test a bit, so if I'm using an OR to set it, what do you think I would use to test it? I know it's like you guys wish that you, hey, oh, sorry, I was off somewhere else. Yeah, an and probably. I bet you guys wish you could take that approach on exams, right? It's like, oh yeah, I think it's this, but it could be something else. I'll check it after the exam. Just, you know, whatever it was, it doesn't matter. All right, to test, we're going to use an and, as Jonas says. So just use an and operator and stick a 1 anywhere we want to see what the value of that bit is. So for example, here, I've got this, right? Are these messed up? I might have copied these from somewhere else. So I want to test this bit. An and's actually going to give you 0. Let's stick a 1 here and a 1 there. So here's my, there's my, what we think is all zeros. Exams are a hoax. You know, Malik, I gotta, yeah, sometimes I agree. And you know, sometimes we just do exams so we have something to grade you on. Like in 412, I mentioned in my 412 course, my mean stack course, there are no exams. There's no quizzes, there's no exams. It's just code. There aren't even any slides. It's literally every day that we meet, like I go through some code and talk about it, and then there's a lot of coding assignments. That's the only grade. I mean, you can either code or not, right? So what else am I going to grade you on? And honestly, like, especially now, like when I went through school, we didn't have the internet. And so we literally just had books and notes from lectures and so on. Like you had to remember stuff if you wanted to work efficiently. But now it's like, we don't have to remember anything, right? I mean, like even this, like if I don't remember something, I just look it up. It takes like a minute to look it up. It takes less time to look it up than it does to find a book. So why are we testing on things that you're going to remember? Well, I really want you to think critically, not remember a bunch of shit. Anyway, sorry for my rant on tests. All right, so that's testing. So here I've got all zeros. Now I'm going to shift over. So I'm going to shift over this value. I set it all zeros. I'm going to stick a 1 in that third position. And then to see if it worked or not, I can just take the value and do an and, a bitwise and, with a mask. This is the mask, M-A-S-K. I know, public education is just bizarre. So weird. We really screwed education up, I think. Anyway, that's the mask. So what I want to know is there a 1 in that third position? That's what that's asking. So it looks like this. Here's the original value. Actually, the original value was all zeros, right? 1, 2, 3, 4, 5, 6, 7, 8. And then we shifted a 1 into that third position here. So if I want to know if that's a 1, just and it with that. If there's a 1 there, I'll get a 1 down here. If there's a 0 there, I'll get a 0. And by masking it out like that, I can do a logical construction like this. So go and do the and. That's going to return a number to me. Value and that bit mask. It's going to return this number. It's going to be a 4 in this case. 4 is positive. Positive values are true in C. And so that's true. Status is success. If it's a 0, so if I got a 0 in that location and I and it with that mask, now what do I get down here in the result? I get a 0. 0 is false in C. And so that becomes false. Status is not equal to success. Cool, huh? And I can generalize it by just doing the shifts. I mean, I guess they look the same, right? Well, all I really did was replace this mask with this shift. Those are the same. I tend to use this syntax because it's easier, at least in my head, it's easier to think about which bit number I'm interested in. Like if I'm reading a specification for maybe it's a motor controller, like a stepper motor controller or something, and it says, oh yeah, so this register bit 7 is the direction bit, which direction the motor's heading. Well, if I think about, bit 7, I got to count over 1, 2, 3, 4, 7, blah, blah, blah. If I just write it like this, and just take a 1 and shift it 7, that's the bit I'm interested in, is the 7th bit over, and I shift a 1 into it, and then I can use that as my mask. What's the B mean? Oh, it just means binary. Sergey. So it just means that this is just like X would mean, X means it's a hex value, B means it's a binary value. Jonas asks, I'm doing it because it's more efficient. Pretty much, yeah. I mean, at this level, like I'm down below bytes, right? I'm down to individual bits in memory, and I can work with individual bits and give those bits meaning. Like the direction of the motor is a single bit. It's either going this way or it's going that way. I only need 1 bit for that. And so like I can check it like this, like which direction is it? Just mask out that bit. Oh, it's 0, it's going to the left. In terms of readability and immediate intuition, I get your, Jonas says, because in terms of readability and intuition and so on, it's like, this is not as readable maybe. I get where you're coming from. But I will say, and unfortunately, I had the advantage of, I've been writing C for 30 or 40 years, like almost since it came out practically in the 70s. This just makes sense to me. Like when I see that, I know exactly what's going on in my head. This maybe, like, I mean, that's obvious too, I guess. I guess, Jonas, my response to that is it gets more intuitive like some of it was a little weird looking, but once you've used it a few times, like you get it, and it becomes a part of you, and it's like you're good to go from that point. It's just, it's like anything, you just got to get used to it. It's like going from a G to a C sharp or to a B flat. It's like that's a really awkward transition, but after a while you get used to it, right? It's like, oh, I can go from G to B flat all day long in the first position. If I want to clear something, well, I used and here with a 1 to check it to see what's in there. If I want to clear something, 0 and anything is 0. So if I want to clear it back to a 0, just and it with a 0. And here I'm doing the same sort of technique, right? I'm taking the 1, shifting it over to that bit position, the third bit position, but then I'm inverting it. So I should end up with a whole bunch of 1s with a 0 in the spot that that I'm not interested in, or that I am interested in. I want to clear it. So I'll end up with a mask like that. When I AND it together, it'll end up 0 and anything is 0, so it'll clear that bit position back to a 0. Malik says, so this is just manual memory management. Yep. It is manual memory management from the C level. Like we're still in C here. This is not assembly language. This is straight up C. In assembler, we'd do the same thing. We would, we'd do logical operators with masks to set or clear bits or test them. It would look exactly the same. And Malik, it's why C is so interesting. Like no other language really, except assembly language, gives you this view of the underlying hardware. Like we're really starting to understand like how is stuff laid out in memory, for example. There's a lot of really low level detail that we have to think about and see that we don't in other languages. I find it fun. I'm an engineer, so I get the little twiddly, the propeller hat. I love this stuff. I love getting down into the bits. But that said, like I love JavaScript too, because it's just a really fun language. It does so much for me that I don't have to think about a lot of stuff. I just think about the application and like the business logic. So it just depends on what I'm writing. If I'm writing low-level controller stuff, I'm going to be in C. If I'm writing really fun web apps, I'm going to be in JavaScript or Swift or something. All right, so let's talk about using these bits as flags. Like here, for example, this is an unsigned short. So I've got 2 bytes basically on most machines these days. That's a lot of bits. That's 16 bits in 8 bytes, in 2 bytes. Well, let's say I just need to keep track of what color something is. I can define them this way. So I can, define red as 1, green as 2, blue as 4, black as 8. Those are powers of 2. If you think about how binary is written, this is the 1's position here, where R is. That's the 2's position. That's the 4's position. That's the 8's position. Next over is 16s and 32s and so on. They're all powers of 2. 2 to the 0, 2 to the 1st, 2 squared, 2 cubed, 2 to the 4th, and so on. Well, if I define my values as powers of 2, that 8 just means that this bit is going to be set to a 1. If I have a blue in there, blue is 4, it's 1, 2's 4, so that bit's going to be set. I can combine them too. So I could have blue and green, 4 and 2. 4 is here, 2 is there. They're individual flags at this point telling me like what's the status of color here. And like look at this. This is an unsigned short, so I got 2 bytes, 16 bits. I'm only using 4 bits here. I could, the next 4 over, I could do another set of these. The next byte over in this unsigned short, I could have 4 of these all together, right? 2 in each byte. So now just in 2 bytes, I've got color information for 4 different things because I'm using single bits as flags. Now, that's not really a disadvantage, but the caveat is like at this level, these aren't numbers anymore. Like if I stick a 1 here in this location, this isn't 8. That is not an 8. It is a bit that is set that tells me something's been turned black. That's it. So I have to, from my programming approach, I have to think of these as individual bits with individual meanings and not some number of some sort. I mean, certainly we could, if you did a memory view of this, we'd see a number, you'd see some number that represent all the bits that are 1s and so on, but that's not how it's being used. We're using it for individual flags. Now this is pretty useful. This is fairly useful. I've actually used this sort of technique quite a bit, especially when I used to write a bunch of controller code. I spent a couple of years writing code to control laboratory instruments to do experiments. And so, at that level, I am controlling stepper motors or sensors or something, and I am using individual bits to mean different things. That's pretty low level coding. From a slightly higher perspective, I might want to use groups of these bits together. Like maybe I want all 4 of these bits to be something called color, and I only need 4 bits for it, or 5 or 9 or something. Like there's some number of bits that I can use to represent some value, but I just don't need the entire byte. Why use the extra bits if I don't need them? So there's a way to do that. It's called a bit field. So a bit field, I can basically define a data type that is a certain number of bits wide. And it's got kind of a funky little syntax. My guess is it was bolted on to C late, pretty early, but after the first C spec came out, I'll actually have to go, I have the Kernighan and Ritchie book in my attic. I'll have to go look at it and see if they had bit fields. It feels like it was something that was bolted on because the syntax is like, ew, why did that happen? It looks like this. So normally we see these inside structs. And the funky syntax is really this little colon over here, and that we're saying these are unsigned int sorts of things. What this really is defining is a struct that has 5 bits associated with day, 4 bits associated with month, and it's an unsigned int, so I got 2 bytes. So that's 9 bits, 9 bits there. The remaining 7 bits I'm going to use for the year. Even though it looks like I have 3 unsigned ints here, this is 1 unsigned int, 2 bytes, and I'm defining bit fields across those bytes to mean stuff. The first 5 bits is the day. The top 7 bits, that's the year. I mean, granted, I have a little bit of a limitation here, right? Because how many years can I store in 7 bits? 2 to the 7th is 128. So I only have 128 years there. I'll probably have to do something else, like maybe I could, use 6 bits for the day, for the year, and have like an epoch or something, so I can add them in. In 6 bits, I can get 64 values. That probably wouldn't work either. But I'd have to screw around with it to get this to be like an actual year, month, day sort of thing. Jonas says, aren't bit fields awkward for the heap? Aren't we always assigning at the byte level? Yeah, we're usually assigning at the word level. Actually, Jonas, you're the perfect student, man. Like Jonas is always like 1 or 2 slides ahead of me in his thinking. Just awesome, because you keep leading me into stuff. Yeah, so that is a problem. It could be a problem. So for example, look at this. So here I've got day is 5 bits, and then month is 4 bits. That's 9 bits altogether. So that actually goes across a byte boundary, right? A byte is 8 bits, and there's 1 bit of the month that is sticking over into the next byte over, because it starts 5 bits in from day, then 4 bits, so that 9th bit is going to be the first bit of the following byte. And if you followed that, like, congratulations. So we might need to align these things. We might need to align them. I'm just going to move this because I had to move it earlier too. So if we're concerned about that, how these fields fall across the byte boundaries, we can either pad them so that they fit, or there's some really cool syntax here. So here I've got some status that's 5 bits wide, and I've got this priority that's 8 bits wide. Well, if I just put them together, so I had this, can I just delete that? Yeah, if I just had that, priority is going to be part of the previous byte, right? And that might be an issue in my code, either the way I'm mallocing stuff, or just the way that bytes are stored. we'll actually see that bytes are stored in reverse order, least significant bit to most significant byte, rather, not bit. So this could be an issue. If we use this syntax, when I put a 0 here, that tells the compiler, hey, look, I know status is only 5 bits wide. This says I want the following field to be aligned on a byte border. So it'll pad 3 bits here so the priority starts in the next byte, at the first bit of the next byte. And so it's not really a 0 length. It's saying, hey, pad this thing out so that I'm all lined up on my bytes. I could do this too. I could just do that and pad it manually, but maybe I don't quite know what the underlying storage looks like. And so if I do that, I'm guaranteed the compiler will do the correct thing to pad out priority so that it starts on a byte boundary. So Jonas, yeah, it's stuff we have to think about, right? So we got to think about what's coming off the heap when we're assigning things. Now, if I'm in, let's say I'm in the process on the assembler side, and I'm using the stack to do stuff, in that case, I'm not really using malloc. I'm just assigning values to memory directly. And so this is less of an issue, although the boundaries might be an issue. But the size of the thing I'm getting back from malloc is not an issue there because I'm not using malloc in the stack. Here's an example, just showing you how they lay out in memory. So I've got day is 5 bits wide, month is 4 bits wide, year is 7 bits wide. So they lay out like this in that byte, 0 through 15. Those are the bit numbers. And then it's a struct, right? So I've got a struct called meeting. The variable is called meeting. It's just, at that point, it's another variable. So I can use the dot notation, just as you would with any other struct, to get into those values. If I want to set the year to 21, it's just meeting.year. Meeting.month, I can set this value. Now somebody asked in A1, what if I tried to do this? So meeting.day, I made 35 instead of 25. Remember, there's no error checking here. And really all I'm doing is laying a number across that bit field. It's gonna I believe, I'll have to check this in the debugger to be sure, but my understanding is it'll overlay. So 35, yeah, that's a 6-bit value, right? And so one of those bits is gonna overlay over into month space. So we have to be really careful to do balance checking and so on to make sure that the thing we're putting in that bit field is the correct size. Let's make it back to 25. 25. So those are the design notes, really. The biggest thing here is that when I'm down at this level using bit fields, and by the way, if I didn't mention it, I will, the Linux kernel, operating system kernels, they're full of this, like bit fields out the wazoo. And it's because we're trying to be really efficient about space. You know, if I can find something that is exactly the right size for what I need, I'm not wasting a bunch of space. I might waste a couple of spaces or, a couple of bits for padding and so on, but I'm not wasting, enormous words to store a single bit. So we'll see structs like this, bit field structs all over the place in the operating system. One issue is that they don't have addresses. The address that we see when we're talking addresses of memory, it's the address of the byte. So addresses are assigned to bytes. There's no sense of, oh, this is at address 0047.2. Like we don't have that at all. It'd be really cool if we did, but we don't. So at a high level, the highest level address we have is for the entire byte. It just means we can't really individually address the bit field using an address or a dereference operator or something. I just can't get to it. What I can do is I have an address for the struct itself. Like I've got a variable that's of type structure, struct date or whatever it was. That I can take a pointer to and then use that address. But then again, like I have to remember, oh yeah, when I do that, I got to use a mask to pull out what's the date, what's the year, and so on. And by the way, just for completeness, if I wanted to know the day here out of all of that mess, what would the mask be? How would I would use an and, right, to mask it out. What mask would I use just to pull the day information out? It would look like this, right? Got 16 of these. Oops. Let's see. That one. Stop it. Stop it. This one. That was like some stupid game. I know. I'll move it out of the way. Shoot. Still do it right here. 1, 2, 3, 4, 5, 6, 7, 8. And then 4 for the month. 1, 2, 3, 4. And then 5 for the day. 5. That's the mask I would use. I would AND this entire byte, 2 bytes, with this. If I ANDed that, this is a mask. And so this would discard everything that it's a 0. It would discard the year and month data. All I would get back would be where the 1s are. So this mask would pull the date out, or the day rather, out of that struct for me. If I wanted to know what the month was, same idea. I would mask out everything else. 2, 3, 4, 5, 5, and the month is 4 wide. 1, 2, 3, 4, 2, 3, 4. So that's the mask if I want the month out of that. Do an AND with it, with whatever the meeting has, AND it with this. And what is that? 1, 2, 4, 8, 16. So it's 32 and 64 is 96. Plus 128 is 218, plus 256 is 400 something, plus 3 something. I don't know what it is. But that's the bit value that I'd mask against to pull out month. And same with year. If I want year, it's all zeros on the right. All, the first 7 bits are 1s. That masks the year for me. So that's how we use masks. It's like, I'm so sorry, but there's one more thing that is going to throw a wrench into all of this. And it's one reason that I tend to just use shifts and that sort of little tilde 1, tilde 0 thing, because I assume that the hardware is going to do the right thing for me. We can't be guaranteed what order bytes are stored in memory. The logical way, if I've got 2 bytes in memory, A and B, and they're sort of, left and right, the natural order would be to store them A, B. That's called big endian. I'm storing the big end of that value on the left, essentially. He wants to know what's the value of the leftmost bit. Well, if we start at 0, so it's how many 1s do I have, how many 2s, 4s, 8s, 16s, 34s, 64s, and so on, all the way across. The largest bit value is all the way on the left. In a big endian system, we store those bytes, big part, little part. That's old school. These days, and by these days I mean since about 1980, everything is stored in little endian format. So if I have 2 bytes, I store them in the reverse order. So if it was AB, I store them BA. The least significant byte goes first, and then the most significant byte. It just has to do with the way the hardware reads memory and what order it hits things. So the problem we have, again, is like, which is it on the platform we're running this software on? Like, sometimes you don't know. If you look at the kernel code of Linux, there are just buttloads of if defs, if def, if def, and all those if defs are around, well, most of them are around what platform am I on? Is it a Solaris platform? If I'm on Solaris, Solaris is a big endian platform. If I'm on Intel, Intel is a little endian platform. If it's an AMD chip, AMD does both. It's bi-endian. It can do either. So it's the operating system that tells the CPU, hey, go into little endian mode. I have to know that that's been told. So more if defs, right? If I'm on AMD and if the AMD chip's been told to do little endian, then I have to order stuff this way. So we have to be concerned about what order things are in memory itself. It's why when we look at memory locations in the debugger, like in CLion or something, we'll see, if we store 5 somewhere, that 5 is over at the left. And then the rest of the stuff is over on the right. Well, it's because it's a little endian. The least significant byte is on the left. That's where the 5 is. And the rest of the stuff, the higher order bits are on the right. And the word comes from Gulliver's Travels. The allegory there was around France and England fighting with each other all the time. And one of the things was there was a huge argument about cracking an egg open to eat it. One country did it by opening the big end first, and the other country did it by opening the little end first. And there were all these laws about when you could do which, and all. They fought wars over it. It was crazy. So that's where Big Indian came from and Little Indian. And this tells us just what I just talked about. So bottom line, we use this stuff a lot, especially low-level programming in C. We'll probably play around with some of this. One of your upcoming assignments is to embed some assembler language into a C program, like a C function. And we'll probably do some bit operations in that, like do some masks so we can pull out stuff from bit fields. So you'll see this again in a couple of weeks. But that's it. That is it. Biggest thing is that you have to remember all this stuff so that your code becomes portable. All right, guys, 3:15. It is time for the weekend. Yay! So I'll see some of you in office hours tomorrow. Otherwise, have a great weekend. If you're celebrating Passover, have a good one next year in Jerusalem. And I will see you all Tuesday of next week. Enjoy. Peace out. No one's moving in here. You guys didn't bake me a cake, did you? That's not my birthday.